Hello everyone, welcome back to our Spark tutorial series. In today's video, we'll explore the concept of the DAG or Directed Acyclic Graph in Spark. The DAG is at the heart of Spark's execution engine, playing a critical role in how tasks are optimized, executed, and fault tolerantly managed across a distributed cluster. If you've ever wondered how Spark processes massive datasets so efficiently, the DAG is the answer. Stay tuned as we break down this concept step by step. Introduction. In Spark, the DAG directed acyclic graph is a vital component of its execution model, representing the logical flow of transformations applied to the data. Unlike traditional execution models, where tasks are executed sequentially, the DAG provides a structured plan of operations as interconnected nodes and edges, with each node representing a transformation and edges showing dependencies between them. This logical representation allows Spark to optimize the execution by analyzing the graph, combining multiple transformations into a single stage, and minimizing data shuffling. What is a DAG in Spark? A DAG directed acyclic graph in Spark is a critical concept that forms the backbone of its execution model. It is a graphical representation where the nodes signify RDDs or data frames datasets and the transformations applied to them, while the edges indicate the dependencies between these transformations. The DAG provides a clear and structured view of the logical flow of operations in a Spark application. 1. Nodes representing data and transformations. In a DAG, each node represents either an RDD or data frame dataset or a transformation applied to it. For instance, when you perform operations like filter or map, Spark creates nodes in the DAG to represent these steps logically. This allows Spark to keep track of every transformation applied to the data throughout the application. 2. Edges indicating dependencies. The edges in a DAG signify the dependencies between nodes. They represent how one transformation relies on the output of another. For example, if a map transformation follows a filter operation, the DAG will show an edge connecting the filter node to the map node, indicating the dependency. 3. Acyclic nature. A DAG is acyclic, meaning there are no loops or cycles. The operations flow in one direction, ensuring that once a transformation is completed, Spark moves to the next logical step without revisiting previous nodes. This guarantees a clear and linear flow of execution. By organizing operations into a DAG, Spark ensures a structured, efficient, and fault-tolerant approach to distributed data processing, making it a core component of its execution model. How DAG works in Spark. The DAG directed acyclic graph in Spark is central to its execution model, dictating how data flows through transformations and how computations are optimized for distributed processing. Here's how the DAG works in Spark. 1. Logical execution plan. Spark constructs a logical execution plan by creating a DAG from the sequence of transformations applied to the data, such as map, filter, or groupie. This graph represents the logical flow of data and captures the dependencies between transformations. Instead of executing operations immediately, Spark records them in the DAG, outlining how the data will flow and how each transformation is connected. 2. Stage division. Spark divides the DAG into stages based on shuffle boundaries. Stages are groups of narrow transformations such as map and filter that can execute without requiring data movement. A shuffle boundary occurs when operations like groupie or reduce by key require redistributing data across partitions, signaling the need for a new stage. Each stage is self-contained and can execute independently once its dependencies are resolved. 3. Task creation. Within each stage, Spark creates tasks, which are the smallest units of execution. Each task corresponds to a single data partition, allowing for parallel execution across worker nodes in the cluster. By dividing stages into tasks, Spark ensures that computations are distributed efficiently across the available resources, maximizing parallelism. 4. Optimization. Spark then applies optimization to the DAG before execution. It combines multiple narrow transformations into a single stage, reducing the need for intermediate shuffles and minimizing the overhead of data movement. This optimization leads to fewer stages and a more efficient execution plan, significantly improving performance for large-scale data processing tasks. In summary, the DAG in Spark provides a logical structure for data processing, ensures efficient execution through stage and task division, and optimizes operations to reduce resource consumption and execution time. This model allows Spark to handle complex distributed computations with ease and scalability. Key characteristics of DAG in Spark. 1. Lazy evaluation. Spark employs lazy evaluation, meaning that it does not execute transformations like map, filter, or groupie as soon as they are defined. Instead, Spark builds a DAG-directed acyclic graph that records these transformations and their dependencies. Actual computation is deferred until an action such as collect or save is called. This approach allows Spark to analyze and optimize the entire before execution, combining operations and reducing unnecessary computation for better performance. 2. Fault tolerance. A key feature of Spark's DAG is its ability to ensure fault tolerance. The DAG captures the lineage of transformations, recording how each dataset is derived from its predecessors. If a task or partition fails due to node failure or other issues, Spark can use this lineage information to recompute only the lost data rather than rerunning the entire job. This mechanism ensures reliability in distributed systems without significant overhead. 3. Parallelism. The DAG structure enables Spark to divide tasks across partitions and execute them in parallel, making efficient use of the cluster's resources. Tasks within a single stage of the DAG are executed concurrently on different nodes in the cluster, leveraging the distributed nature of Spark. By organizing transformations and dependencies in the DAG, Spark ensures that parallelism is maximized, significantly improving the speed and scalability of data processing. These characteristics make the DAG in Spark a powerful framework for handling large-scale distributed data processing while ensuring efficiency, reliability, and fault tolerance. Example of DAG in PySpark. This example demonstrates how Spark constructs and executes a DAG-directed acyclic graph through a sequence of transformations and actions applied to a dataset. Here's a step-by-step explanation. Initialization. The process begins by initializing a Spark session, which serves as the entry point for working with PySpark. A data frame is then created from a list of data containing names and ages, representing a simple dataset with two columns, name and age. Building the DAG transformations. Several transformations are applied to the data frame, and Spark builds the DAG during this process. Transformation 1 filter. The first transformation filters the data frame to include only rows where the age is greater than 30. At this point, Spark does not execute the operation, it merely records this transformation in the DAG. Transformation 2 add column, a new column. Age underscore in underscore 10 underscore 10 underscore years is added to the filter data frame. This column calculates the age 10 years into the future for each filtered record. Again, Spark records this transformation without executing it. Transformation 3 grouped by the filtered and augmented data frame is grouped by the age underscore in underscore 10 underscore years column, and the count of records in each group is computed. Spark adds this operation to the DAG but does not execute it yet. Triggering the DAG action. The show action is called to display the results. This action triggers the execution of the DAG, prompting Spark to compute the transformations recorded earlier. Spark processes the data in the sequence defined by the DAG, executing tasks in parallel across the cluster. Execution and output. During execution, Spark applies the filter, calculates the new column, groups the data by age underscore in underscore 10 underscore years, and counts the records for each group. The results are then displayed on the console. This output indicates that two records were grouped into age underscore in underscore 10 underscore years values of 45 and 50, each with a count of 1. This example showcases how Spark optimizes and organizes data transformations for efficient execution, deferring computation until an action is called. It also demonstrates Spark's ability to process transformations and tasks in parallel across a distributed environment. Advantages of DAG in Spark. 1. Optimize execution. The DAG directed acyclic graph in Spark enables highly optimized execution of data processing tasks. By analyzing the sequence of transformations, Spark combines multiple narrow transformations such as map and filter into a single stage. This minimizes the overhead associated with shuffling data between stages, reducing the time and resources required for execution. As a result, the DAG helps Spark execute tasks more efficiently, ensuring faster processing of large data sets. 2. Fault tolerance. A key advantage of the DAG is its ability to ensure fault tolerance. Spark uses the lineage information captured in the DAG to track the dependencies between transformations and datasets. If a partition of data is lost due to node failure or other issues, Spark can efficiently recompute the lost data by re-executing the relevant transformations recorded in the DAG. This mechanism avoids the need to reprocess the entire dataset, ensuring reliability and reducing recovery time. 3. Parallelism. The DAG architecture facilitates parallel execution of tasks, which is one of Spark's core strengths. Each stage in the DAG is divided into tasks that are distributed across worker nodes in the cluster. These tasks operate on separate partitions of data, enabling Spark to utilize the full capacity of the cluster's computational resources. This parallelism not only improves performance but also ensures scalability for processing massive datasets. These advantages make the DAG in Spark a critical component for achieving high performance reliability and scalability in distributed data processing. By leveraging optimized execution, fault tolerance, and parallelism, the DAG enables Spark to handle complex workloads efficiently and effectively. That wraps up our discussion on the DAG in Spark. We learned how the DAG optimizes execution, ensures fault tolerance through lineage, and leverages parallelism for efficient distributed processing. Understanding the DAG is key to mastering Spark and making the most of its capabilities. If you found this video helpful, don't forget to like, share, and subscribe for more content on Spark and big data technologies. See you in the next video.